So when we first learn about integrals, the way we learn really to compute integrals is by using the fundamental theorem of calculus, which, if you remember, can kind of be written like this. The integral from a to b of d dx of some function f of x dx, this is equal to f of b minus f of a. Okay? Now, of course, when you actually learn the fundamental theorem of calculus in class, usually you just have a regular f here and a capital F here, which is an antiderivative. But if we put the derivative here already, then little f is a derivative or an antiderivative of df dx. Right? But I want to show you sort of another way to think about what this is doing. Right? So we're integrating here over, so we're integrating over this interval a to b. Okay? Now what is the boundary of that interval? Okay, so the boundary of this, so this is a common notation for the boundary of a surface or a curve or something like that. Right? So the boundary of this thing consists of the 2 points A and B. Right? Because what does this look like? Well, if we have a number line here, we have a closed parentheses at, or a closed bracket at A and B. And everything in the middle is, this whole thing is the interval now. And if we only want the boundary, we want kind of the things at the edge, right? And that would be these 2 points. When we're taking the boundary of something, though, it comes with something called an orientation, right? And we'll talk a little more about this in a couple videos from now. But when we're taking the boundary of a one-dimensional thing, the orientation kind of comes with a plus and a minus. A plus on sort of the positive end, well, I don't know if I should call it positive end, but the right end, and a negative at the left end. Or in other words, if we interpret this as the start and this the finish, the start has a minus, the finish has a plus. All right? So what is the point of this? Well, the point of this is that we're switching the derivative of the function for the boundary of the thing we're integrating over. That's kind of the theme here. All right? So this thing here, you can kind of think of in a way as an integral over these 2 points. And I'll just say when you take an integral over a discrete set of points, that's just a sum, a finite sum. Well, it could be infinite, but a finite sum here. All right? So that's what the fundamental theorem of calculus should be interpreted as, is switching a derivative for a boundary, right? And that's why it's f of b minus f of a, right? The a has this minus encoded in it. All right? So now we have another theorem in this theme, the fundamental theorem of line integrals. Right? So this, in a sense, really is a generalization of the standard fundamental theorem of calculus. Right? So what does it look like? So make sure I don't forget anything here. So let C be a smooth curve given by R of t from A to B. Okay? And then we're going to let f be a differentiable function whose gradient is continuous. Kind of ran out of room there. Let me just move that down to the next line. So is continuous on C. Right? Then what do we get? Well, we get something that's a generalization of this. And what that is it's the integral over C of the gradient f dot dr, right, equals f at r of b minus f at r of a. Right? So we see that same thing. Right? We switched the derivative, which in this case is the gradient. We switched the derivative of the function for the boundary of the curve C. Right? So that curve C is something that's just floating around here. And here we have r of a, and it goes this way. And it ends at r of b. Right? So the orientation of the curve is the direction here. So it's going to be the end minus the beginning would be the orientation on the boundary. And the boundary of C, let me call this point A and this point B just for simplicity. Then the boundary of that curve C is just given by A, B. Right? And since this is the beginning, it has sort of a minus orientation. And since that's the end, it has a plus orientation. All right? So this really is, in complete honesty, a generalization of this. In fact, I'll give you the challenge here. Think on your own how to do this. How can you recover this exact statement from this one? So think about that. And we'll move on to an example. Actually, real quick before the example, let's prove this guy. It's really not so bad. Right? So the proof of this, so we have to actually integrate this guy. So remember how to do that. This is just the integral from a to b of gradient f of r of t dot product with r prime of t dt. Right? But now you may remember this is just the chain rule. Right? This is the result of doing a chain rule derivative. So this is just the integral from a to b of d dt of f of r of t. 1, 2, 3. Okay? Then, now it's just the regular old fundamental theorem of calculus. We're integrating the derivative, so we get f of r of the top one minus f of r of the bottom one. Right? And that's all there is to this proof. That's all. Okay? So pretty simple one, but just wanted to show you that real quick. So let's compute this example. Right? We're trying to compute a line integral along C of ln y plus 2xy cubed dx plus 3x squared y squared plus x over y dy. Right? And that curve C has parametric equations given by x equals a half t squared plus 2 and y equals e to the t times 1 plus 2t minus t squared. And this is as t goes from 0 to 2. Well, let's have a look real quick. If we start plugging in, well, y into here is already a mess, and then x into this stuff. So this is going to already be a mess when we plug in the curve to the integral. So there's maybe a better way to do this. Right? And that better way would be the fundamental theorem of line integrals. Right? So this integral up here, we can think of it as the integral of f dr, where f is given by ln y plus 2xy cubed and 3x squared y squared plus x over y. Right? X over y. Right? But to use the fundamental theorem of line integrals, we have to ask, is this equal to the gradient of something? In other words, is that a conservative vector field? And, you know, it's not obvious, right? So how can we check such a thing? So let's write down a general statement here. So the gradient of f is given by fx, fy. Okay? If we have a vector field f being pq, just sort of generally, that means fx should be p and fy should be q. Well, we know we have this property, fxy equals fyx, as long as f is c2, right? But fxy is nothing but py, and fyx is qx. If these two are equal. So in other words, if py is equal to qx, and f here, this should be a C1 vector field, right? So p and q are both C1 functions. If that's true, then we can expect that f might actually be a conservative vector field, all right? Well, so usually the easiest way to do this is to just try and figure out a potential function. So let's try and do that here. Right? So, sorry, if f is conservative, meaning it's the gradient of some little f, remember that little f is called a potential function. All right. Well, so let's just assume now that this is conservative and see if everything works out. Okay? If it's not conservative, what we're about to do is going to break somewhere. But let's see what happens. Right? So assuming it is conservative, then let's say we integrate p to try and find f. Right? Then what variable do we need to integrate p with respect to? Well, p should be fx, so I should be integrating it with respect to x to get f back. All right, well, if I integrate that with respect to x, ln y is just a function of y, so it's a constant for x, and I get x ln y. All right, if I integrate 2xy cubed, I just get x squared y cubed. All right, but now here comes the interesting part. I've integrated with respect to x, so hopefully you remember. That means that I get some function of just y left over now, right? And again, that's because to get back to p, I should be taking the partial derivative with respect to x. And this kind of thing is completely gone when you do that. All right, well now I have what I think f looks like. So that means if I take f, the partial derivative of this with respect to y, well, I'm going to get x over y plus 3x squared y squared plus, now it's partial derivative with respect to y, so this is g prime of y. Right? Since this only has one variable, saying g prime makes sense. Right? And that's fy. Fy should be q. So we're asking now, is this true? Well, what is q? It's 3x squared y squared plus x over y. So let's match things up. we have a 3x squared y squared on both sides. We have an x over y on both sides. So what does that say about this guy, g prime of y? Right, so that says g prime of y is 0. Well, we still need to solve for g, so that means g of y, well, if we integrate this, we just get, well, the integral of 0 dy, so that's what g prime is, so we just get some constant. Right? Now, so this is going to tell us now every potential function. So if we write down f equals x ln y plus x squared y cubed plus c. So that's a whole family of potential functions, right? And we only actually need one potential function. So you can choose c to be whatever you want now, because we just want one potential function. We don't need a whole family. So let's go ahead and say it's c is 0. Okay? All right, so we found a potential function whose gradient is this guy. So now we can actually use the fundamental theorem of line integrals. All right, but that means we need the start and end point of this curve. So let's do that over here real quick. So c at t equals 0, well, x is going to be, where's x? Up here. Just 2. Y is going to be e to the 0 times, well, 1, right? So this is just 1, right? And then at t equals 2, we get, so x is 2 times 2 is 4, divided by 2 is 2, plus 2 is 4. And y is e squared, 1 plus 4 minus 4, so e squared. Right? So that means when we finally finish up this integral here, so that line integral of f dr is going to be this new f we found of the end point, so that's this one here, 4 comma e squared, okay, minus f at the start point, which was 2 comma 1. Right? So now we just have to plug all that stuff in. So plugging in that here gives me 4 ln of e squared. Well, ln of e squared is just 2, so that's 8 plus some number here, 16 e to the 6th, okay, minus, now I plug in 2, 1, so 2 ln of 1 is 0, so that's out, and then here just 4 times 1 if you like. Right, so I get 4 plus 16 e to the 6th. Okay? So hopefully this idea here made sense of, we have this line integral here which looks kind of messy, and we don't really want to do it as it stands. So let's check if that vector field is conservative, because then we can use the fundamental theorem of line integrals. Okay? Hopefully that all made sense, and I'll see you in the next video.